students, how are you? So I'm back. I'm Krishnendu Roy once again. Now I will be teaching you. Basically, we are following tutorial series of our Unit 1. So till now we have covered 2 tutorial classes for Unit 1. So this is the third tutorial. Okay, so and I hope that you are learning properly the this particular course, because this particular course is not only good for this syllabus and means this BTech course, but it also will give you a very much confidence when you go for the interviews, because you know anything you do, you cannot omit a thermal from your scenario, from the scenario of design. So learning thermodynamics, learning it allied courses like heat and mass transfer, and then the refrigeration and air conditioning, then the power plant engineering, these are actually which you if you command these subjects, they will actually give you a bit of confidence, in fact more of confidence when you are actually into the field and when you are up for the interview. Okay, so heat transfer should be taken very seriously. It's a full credit course. So to make you go to do this thing very cautiously, to make you learn many more things, particularly the numerical aspect, because many of the students are afraid about the numerical, and many of the students are afraid about the subject just because they are reluctant to solve the numerical. So here I am once again back to make you solve the numericals for this particular subject, which is heat and mass transfer. Okay, it's KME 501 in mechanical engineering course. So here we are into the third tutorial for the Unit 1. So let's get into it. Okay, so the first numerical once again with the composite wall. Okay, the metal plate of 4 mm thickness K is equals to 95.5 watts per meter degree Celsius is exposed to vapor at 100 degrees Celsius on one side and cooling water at 25 degrees Celsius on the opposite side. First stop, the heat transfer coefficient on the vapor side and water side are 14,500 watts per meter square degree Celsius and 2,250 watts per meter square degree Celsius respectively. Determine the rate of heat transfer. The second thing, the overall heat transfer coefficient, and the third thing, temperature drop at each side of the heat transfer. Okay, so in all my videos I have been doing this, so I'm continuing that particular I'm just continuing that particular topic once again in this video. So basically we are again into composite wall, but very soon in this video itself we will be going for the heat transfer through composite cylinder. Okay, so here what you can see in this diagram that there are two composite walls, means there are two material that's when conjointed is becoming one composite wall. Okay, so here it is, it's vapor. Okay, so what's there is the metallic plate of 4 mm thickness. The metallic plate of 4 mm thickness here, metallic plate of 4 mm thickness is exposed to vapor at 100 degrees Celsius. So this is basically vapor, so it's basically open and it's basically the ambient to this wall. Okay, the other side of the ambient to this wall. Okay, and the other side is water. Okay, so one side is vapor and the next side is water. Okay, and the cooling water at 25 degrees Celsius on the opposite side. The heat transfer coefficients on the vapor side. Okay, the heat transfer coefficient, see when you are looking at this particular unit, you should be aware whatever be the title of this means whatever be the name, like it could be like heat transfer coefficient, it could be like convective heat transfer coefficient, or it could be like anything. But if you see this particular unit means watts per meter square degree Celsius or watts per meter square Kelvin, then basically he is talking about H. Okay, so H is basically that is the heat transfer coefficient from Newton's law of convection or the Newton's law of cooling for the matter. Okay, so this is vapor and this is water and this is metallic plate, so it is getting sandwiched between the vapor side and the water side, and how to make the thermal resistance, right? So to make the thermal resistance circuit, the analogous circuit of the thermal resistance in thermal circuit, you need to know that this is the HF, that is the vapor side resistance. So it will be R thermal convection of vapor side, then it will be of the material side, means the metal plate, and then the heat will encounter once again the the convection thermal resistance of the water side. So the heat will first of all encounter the thermal resistance of vapor, then it will enter into the metallic plate, it will encounter the thermal resistance due to metallic plate, and once it comes out, it will actually encounter the thermal resistance or the convective resistance of water. So that is how it's being made. 100 degrees Celsius, heat is getting transferred here, okay, to 25 degrees Celsius. So this is how you actually make similar to what you do in the electrical circuits. Okay, this is the solution there. Okay, the thickness of the metallic plate. The thickness of the metallic plate is given here. So it is like L is equals to 4 mm. So you need to convert it into meters. Okay, the thermal conductivity of plate material. Thermal conductivity of plate material is also given here. The temperature of vapor, hot fluid. The temperature of vapor is also given here. Okay, so it is 100 degrees Celsius. Okay, the temperature of water, cold fluid. The temperature of cold fluid is also given here. So you have almost everything. The heat transfer coefficients of the vapor side, when the heat first of all encounters, the first thing that comes in is the vapor side, and the vapor side has the heat transfer coefficient of this value. It's a good value because it's hot. Okay, and water side, and when the heat comes out of the metallic, when the heat encounters the when the heat comes out of the metallic body, it actually encounters the thermal convective resistance of the water, and the value of the thermal convective resistance of the water is 2250 watts per meter square degree Celsius. Okay, the rate of heat transfer per meter square, and you all know that this is, you all know from my previous videos that this is of the format of delta T by RTH. I have already told you several times that it can be written like this. So RTH for conduction is L by Ka, okay, and RTH by convection is 1 by HA. Okay, so here we will be using almost everything because we have convection on two sides and we have conduction on one metallic plate. Okay, so here it is. So you can see it is convection, convection, and there is the conduction. Okay, so put all the values here. It is 100, it is 25, so it is 1 by H. So A has been, because you have to calculate per meter square, so that's why the A has been taken out. So it is like only 1 by H, and it is only L by K. Okay, so you can see 1 by H vapor, 1 by H cooling water, and it is L by K. Okay, so just put all the values here. It is 75, and this is the 1 by H, this is the 1 by H for the cooling water, and this is L by K. So just a simple mathematics, and you can calculate the rate of heat transfer is this much. Q is equals to 1.35 into 10 to the power 5 watts per meter square. So it is very much simple. Okay, so it's very simple to understand that how, you know, when you have a convection, along with the conduction, so how you first of all convert it into an electrical resistance circuit. Look at it, how you convert it into an electrical resistance circuit, and then because it will be in series, and something if it is in parallel. I have already shown that kind of numerical. I have solved that kind of numerical in my theory lectures, in my theory videos. You just go and check it out. Okay, there was you know, two elements were in parallel, so you just you know, go for like okay, I will solve it later on. Okay, so there were, you know, two things that they were in parallel, and then you go for the equivalent resistance, and equivalent resistance will be like 1 by R plus summation of 1 by R. You all know. Okay, now the next thing, the overall heat transfer coefficient U, the rate of heat transfer through a composite system is given by, we all know that Q is equals to UA delta T. Okay, so delta T will be T hot minus T cold, or it could be Ts minus T infinity, whatever be the condition in the numerical. Okay, so now the overall heat transfer coefficient. So the overall heat transfer coefficient from you know, what I taught you in the video lectures, in my theory lectures basically. So I already told you that U is equals to 1 by summation of all the resistance. It's the reciprocal of summation of all the resistances. So here you will find out. So it is like the overall heat transfer coefficient. Overall heat transfer coefficient will be Q is equals to UA delta T, as I have already told you here. So it will be like this. So you already have Q. You have Q by A rather. Okay, from the previous thing, you have Q by A watts per meter square. Okay, just put it here. you have delta T. So just solve U. It's a simple mathematics and it's simple numerical. Now temperature drop on at each side of the heat transfer. Temperature drop at each side. Now what do you understand by temperature drop at each side? Let's see this. We know that Q is equals to QH is equals to Q of 1 to 2, okay, and QCF is equals to 1.35. So what he's talking about actually, I already mentioned it several times in my lectures that it's a steady state. Here also I have mentioned, see the Q that is entering here, it's a steady state, it won't change. So actually it will come in and it will go out with the same magnitude. You just have to take the intermediate heat, the parameters, so that you can adjust to get the same amount of heat. Okay, I have told you in the in my previous lectures several times. So here also we are doing the same thing. Here also see Q is equals to QHF, Q1 to 2, that's the metallic plate, and Q cooling fluid, so it remains same. Okay, so just you need to take it out, temperature drop at each side. So on each side there will be you can adjust it like T1 minus T2 by thermal resistance, that will be equal to like T3 minus T4. I am taking just an example. Thermal resistance, it could be conduction, and T4 minus T5 by thermal resistance, it could be convection. So everything will remain same. Okay, this is all Q, so the Q will remain same. The only thing is that you need to either calculate RTH separately and can find out the temperatures, and whatever is asked you can actually do it like this. So here also we have done the same thing. See, Q12 is just the simple mathematics that they have done. Okay, is delta THF. Okay, and then the temperature drop in the metal they have calculated as 5.65 degrees Celsius. Okay, and then the thing for cooling fluid. Now since they have done it for heating fluid, so heating fluid heat has been taken up. Okay, the temperatures regarding the heating fluid has been taken up, and if you want to do for the cooling fluid, so the cooling fluid temperature is being taken up, and we all know that QHF, Q12 and QCF, they are all same. So only they are playing with the temperatures and the resistances. Okay, only they are playing with the temperatures and the resistances, rest everything is same, because again I am saying the heat is steady in nature. So heat that is coming into the system will go out of the system with the same magnitude. You just need to play a game with temperatures and the resistances. That is it. See, the same thing has been done. So temperature drop in the water film has also been calculated with the same principle. Okay, now let's talk about another numerical. The interior of a refrigerator, having inside dimensions of 0.5 meters by 0.5 meters base area and 1 meter height, is to be maintained at 6 degrees Celsius. The walls of the refrigerator are constructed of two mild steel sheets 3 mm thick. K is equals to 46.5 watts per meter degree Celsius with 50 mm of glass wool insulation. K is equals to 0.046 watts per meter degree Celsius. Between them, okay, if the average heat transfer coefficients at the outer and inner surfaces are 11.6 watts per meter square degree Celsius and 14.5 watts per meter square degree Celsius respectively, you need to calculate the rate at which heat must be removed from the interior to maintain the specified temperature in the kitchen at 25 degrees Celsius and the temperature on the outer surface of the metal sheet. See, again everything will be same, only thing that the values have changed and the numerical has changed, and rest everything will be same. Okay, so this is again a case of a composite wall. Now I have been doing composite wall from you can say from my from my previous 3 lectures I have been doing this composite wall. So I hope that the concept of composite wall it comes into your mind very tightly, and I don't think you will now be able to forget. Even if you want to, you won't be able to forget the concept of the thermal resistance, the concept of Fourier law of conduction, the concept of Newton's law of convection, the concept of thermal resistance when you combine these convection and conduction, okay, and the composite wall along with the convection on both the sides. So these type of numericals are very important. So I have already done about 10 to 12 numericals, and I have been doing it from my first video that I have taken in. Okay, so let's do this. So this is a mild steel sheet. This is a mild steel sheet here. Okay, this is a mild steel sheet. Once again, to reduce the heat transfer, they have introduced glass wool. Okay, to reduce the heat transfer, they have introduced glass wool, and we all know that the glass wool is actually an insulator. It actually obstructs the heat. Okay, so if you know time process, I will tell you what is insulation, but till now, means for this time, you just take that the glass wool is an insulation, and this is how you can actually reduce the heat from here to here. Okay, now what's happening is, see, this everything is given. LA is equals to LC. Okay, thickness is given. This is C, this is A, 3 mm, 3 mm each. L of B, the thickness of glass wool insulation has also been provided. Okay, Ka is equals to Kc. Okay, means this the since they are all they both are mild steel sheets, so definitely thermal conductivity remains same. Okay, and Kb, that is the thermal conductivity of the glass wool, is also given. We have Ho, that is Ho is here, outside surface of the refrigerator, means the heat transfer coefficient for the resistance you want to calculate. Okay, and To, that is the outside temperature, you can say the ambient temperature is 25 degrees Celsius. Okay, and Ti, that is the inside temperature of the refrigerator, is 6 degrees Celsius. Okay, the total area through which heat is coming into the refrigerator is this one. Okay, plus this, so it is like 2.5 meters square. Okay, so how you actually got this? This is this. Okay, and what else? And what else they might have calculated? See, this is like 0.5 into 0.5 into 2. Okay, and then that's the base area, basically that's the base area. Okay, there's the front area and the base area. Okay, so once you, because the refrigerator is a complete enclosure, so the heat is coming in from all the sides. So from the top area, from the base area, from the front area, everywhere the heat is peeping into the refrigerator. Okay, so that's why the insulation has to be insulation has to wrap all the inside surfaces from the refrigerator, otherwise there will be heat penetration, and whatever you wanted to cool in the refrigerator will actually gets heated up. So that's a menace, and that's what you don't want when you have a refrigerator working at your home. Okay, the rate of removal of heat Q, the rate of removal of heat Q is equals to Q is equals to, it is the same thing, see. Okay, so it's ATO minus TI, and since you have 3 portions for the conduction, so there are 3 conductive resistances, and since you have an outside ambient and an inside ambient, so there will be 2 convective resistances for both the ambient separately. So see, it is 1 by Ho, it is 1 by Hf. So you put all the values here, see, you have all the values put in, you will get the 38.2 watts, means this is what the heat that you will calculate by simple mathematical relation. Okay, now the temperature at the outer surface of the metal sheet, the temperature of the outer surface of the metal sheet is actually, this is actually nothing but the convection. You can actually calculate it by the convection. What's happening is, see, here there is, suppose, a temperature at the external surface. Okay, and here you have a temperature, so it will be like T minus Ti or Ti, right, or the outer surface will be this. Okay, so you have it here. Okay, so it will be T minus To. Okay, so that's pretty simple. So look at it. So here you go, just apply the Newton's law of convection, and with the Newton's law of convection you can calculate the temperature that is on the surface of the refrigerator. I hope with this numerical you came to know about, till now I have been doing such kind of numerical for composite walls, for simple brick walls, for including convection and conduction, okay, both combined. So I hope by this tutorial you must be able to understand everything, because this is pretty important topic that I have been covering from my past all the videos. Okay, so this is very important. So let's look at the other primary objective of learning conduction, because there's not only a slab or a rectangular object, there is also cylinder and also there is a sphere. So let's talk about heat conduction through hollow composite cylinder. Okay, so here it is. So it's a cylinder, so it's a hollow cylinder of length L. Okay, so heat radially flows outwards. So this is the inner radius, this is the outer radius, and if we take an element, so the radius of the element is r, so inner radius r1, external radius r2, and from the center if we take the radius of the element, so it is r. So okay, so no heat flows in the axial direction. Okay, so this is all about the diagram. So let's talk about how to derive this. Okay, and you need to note down the thermal resistances, the thermal resistance of conduction through a hollow cylinder. Okay, so till now what you have learnt is a thermal resistance, when heat is getting transferred through a slab. Okay, that's L by Ka, but now it's something else. Now area through which heat is transmitted is 2 pi Lr, 2 pi Rl, you all know that is the surface area. Okay, the path length dr over which the temperature falls is dt. Here it is. Okay, here. Now q is equals to minus Ka dt by dr, as it has a radii, so that's why dx is now replaced by dr. Okay, just this is the area, this is the thermal conductivity, and this is basically Fourier's law of conduction. Okay, this is dt by dr, this is temperature gradient in the cylinder because it is having a radius. Okay, so here it is, integrating on both sides. Okay, so it is dr, so dr by r has been made subject on the left hand side, and dt is being left alone and has been made subject on the right hand side. So since they both are integral operators, so you need to integrate them. So just have the integration. 1 by x, it is ln x. Okay, integration of 1 by x is ln x, so you just put this, so you will get like natural log of r2 by r1, and here it is t, because it is just dt, so it will become t after integration, and after putting these two like t2 and t1, it will be like t2 minus t1. Okay, so it will be ln r2 by r1 is equals to minus k 2 pi l t2 minus t1. So if suppose if we stack this in this format, so we already have t1 minus t2 here. Okay, we already have q here. So what's remaining? The remaining portion will be the RTH. So RTH will be ln r2 by r1 divided by 2 pi kl. So now from now onwards, this thing you need to remember. Till now what you have remembered, what you have seen is L by Ka, because we have been solving numericals of slab, we have been solving numericals of rectangular elements, so that's why it was L by Ka. But now we will be solving, from here onwards we will be solving numericals of cylinder, composite cylinder. So this will be this will have the resistance of ln r2 by r1 by 2 pi kl. Okay, now let's talk about a numerical. It's a simple derivation, just integrating on both sides and getting the answer. Okay, now let's talk about the numerical, and as you can already see, now this is a cylinder. Okay, this is not a slab. A steam pipe, inner diameter 150 mm and outer diameter 160 mm, having thermal conductivity 58 watts per meter degree Celsius, is covered with two layers of insulation of thickness 30 mm and 50 mm respectively, and thermal conductivity is 0.18 watts per meter degree Celsius and 0.09 watts per meter degree Celsius respectively. The temperature of inner surface of steam pipe is 320 degrees Celsius, and that of the outer surface of the insulation layer is 40 degrees Celsius. So determine the quantity of heat lost per meter length of steam pipe and layer contact temperature. Okay, so what's given? Okay, so the diameter is given, so definitely you need to find out the radii. Okay, so the first radii and the second, okay, inner diameter, outer diameter. So the inner diameter and the outer diameter. Okay, so radius has to be calculated. Now the R3 is this, see, this is R3. So R3 will be 80 plus 30. Why 30? Because 30 mm of first insulation is being there. Okay, so after R2 there will be 30 mm added to it. So this is R3. Now R4, after R3, here is this is the fourth one. So after R3 there will be the thickness of that insulation will be added. So it is 50 mm here. so it is 110 plus 50. So R3, R4, R2, R1. You have you have deduced all the radii from this numerical. Okay, so let's start about. So everything is given, T1 is given, T4 is given, Ka is given, Kb is given, and Kc is given. So what is Ka, Kb, Kc? So here it is written steam pipe Ka means A, insulation is B, here is the insulation, and another insulation, that is C. So all the thermal conductivities are actually given. So quantity of heat loss per meter Q and layer contact temperatures T2 and T3. And I have already told you several times that what to do when you need to calculate the layer contact temperature. See, now everything has changed here. Till now you have been doing like 1 by H plus L by K, something like that. Now here it is ln by this by 2 pi KL. Okay, so 2 pi L has gone up because 2 pi L is actually the area. Okay, so what you need to do is, so here it is, this is the resistance, these are the resistances. Okay, you just give all the values here, you have all the values here to calculate this also. And you all know that I have been explaining you so many times that the heat remains steady, so it goes on. Okay, you just have to play with the resistances and the temperatures. So here also you will do the same thing, and with this you can actually, with the simple mathematics, you can calculate the contact temperature. See, the same thing, the Q entering here is going out, so you just have to play with the contact resistances and the temperatures. See, the concept is same. Okay, a steam pipe K 45 watts per meter degree Celsius having 70 mm inside diameter and 85 mm outside diameter is lagged with 2 insulation layers. The layer in contact with the pipe is 35 mm asbestos. Okay, K is given, and it is covered with 25 mm thick magnesia insulation. Okay, this is the K for that. The heat transfer coefficients for the inside and outside surfaces are this and 6.5 watts per meter square degree Celsius respectively. If the temperature of the steam is this and the ambient temperature is 30 degrees Celsius, the steady loss of heat for 50 meters of pipeline, that you need to find it out, and the overall heat transfer coefficients based on inside and outside surfaces of the lag steam. So first of all, deduce the radii. Okay, deduce the radii, and I have already told you how to do it. Just add on the thickness of the insulation after the radius, the first radius. Okay, so here it is R1, R2, that is already given. So just, and then the addition of the insulation thicknesses, the length is given, Ka, Kb, Kc is already given. Okay, this is the temperature of the steam given, the ambient temperature is given, the heat transfer coefficients are also given. Okay, so what do you need to do? The same thing. See here, the heat transfer is heat getting transferred through the composite cylinder, so the resistances has changed, and since now it has convective resistance as well, so now it is accompanying with the convection. So just put all the values here, put all the values here, and then you can find out the value of this heat. And again the heat transfer coefficient UO or whatever, so you know that it is Q is equals to UA delta T, be it outside or be it inside. So the formula remains same, the only thing that changes is the area. So if you have to find out UO, yani overall heat transfer coefficient of outside surface, the area has to be of the outside surface, means the outer radius, and if you have to find out the overall heat transfer coefficient of inner surface, the area has to be of inner surface. So it will be the area of the inner surface, means of the internal radius you need to calculate. So this is how you will calculate. Okay, on the similar lines, this is another numerical. So everything is given. So this is R1, R2, R3, Ka, T1. The total heat loss per hour you can actually calculate, as I have already mentioned you several times. Okay, so just with this you can calculate the total heat loss per hour. Okay, the total heat loss per meter square of the pipe surface, this is per meter square, means you have to divide it by 2 pi RL, that is the area. Okay, the total heat loss per meter square of the outer surface, so that is the outer radius. So just you need to play with the radii, and you can get the inner heat loss on the inner surface and heat loss on the outer surface. Okay, it is R1 and it is R3, as you can already see. The temperature between two layers, you can see the Q remains same, you just playing with the temperatures and the resistances. So here you can get the T2, so this is the interfacial temperature, and this is how you can get. So finally what we have done today is I have tried to explain you the heat transfer, the conduction through a composite cylinder. First of all, we basically derived the heat transfer through the heat transfer, the conduction heat transfer through a hollow cylinder, and then we tried to we calculated the heat transfer to the composite cylinder, and this is very important as we did the heat transfer for the rectangular slabs and the composite structure of those slabs. Thank you, and I hope you will have a good day ahead. Thanks a lot.